Welcome back everyone. So today I picked up another problem from fluid mechanics chapter from Pathfinder. It's question number 19 from build up your understanding section. So it will test your buoyancy force understanding, and all over I guess hydrostatic pressure related concepts will also get revised through this problem. So let's read the problem first. Two objects of equal volume V equals to 1 meter cube and densities rho 1 equal to 400 kg per meter cube and rho 2 equal to 600 kg per meter cube have identical flat portions of area S equals to 100 centimeters square on their surfaces. These flat portions are glued to each other. The composite body thus formed floats fully submerged in a liquid with the common flat portion horizontal as shown in the figure. If the glue can withstand a maximum force F equals to 500 Newton, at what minimum depth h in the liquid can the common flat portion be in equilibrium, keeping the objects intact? Acceleration of free fall is g. So let me just draw the diagram once again here. So let's say this is the liquid surface, and say this is the composite body. One is of density rho 1 and another one is of density rho 2, and the liquid is having density rho. Let's say both these are volume V and V. So now we'll take the composite body as a system, right? We're taking the composite body as a system. We can apply the net force is equals to 0 as it is in equilibrium. So the net upward force will be the net buoyancy force. It will be 2V into rho times G, that is the weight of the fluid displaced, and the weight of the composite body will be rho 1 Vg plus rho 2 Vg. From here we will get that rho equals to rho 1 plus rho 2 upon 2. So that's the first step. We are done with this. We have found out the density rho of the fluid in terms of rho 1 and rho 2. We'll use it later on whenever rho value is required, right? So next I will try to draw the FBD of the two parts separately. Okay, so let's say this one, this one is the first part, which is having a density rho 1, and this is the second body having density rho 2, and these two surfaces are flat. So basically what's the buoyancy force? The water will exert a hydrostatic force from all the directions, and a net hydrostatic force due to pressure difference at different heights will just result in a net upward force in this direction, right? And that is what buoyancy force is. This is the origin of buoyancy force. It is just the hydrostatic force, and as different heights will have different pressure values, so whenever you will go down the depth, the pressure value will increase and automatically the force will also increase. So there will be a net upward force that will create the buoyancy. So we have found out that buoyancy is weight of the displaced fluid. So in this case the volume is V. Here also volume is V I'm writing, and this volume is also V, as the dense liquid of density rho is all around this body. So we think that there should be a buoyancy force having the value rho Vg, but it's not. Why not? Because in this lower portion there is no water, so there is such an amount of force that would have acted if there was some water. So let's say this upper surface's hydrostatic force will sum up to a force of F1 in downward direction, and these forces, the forces acting on the horizontal surface is, let's say, F2 in magnitude. So F2 minus F1 would have been the net buoyancy force, that is rho Vg, but here F2 is absent, right? So the buoyancy force will not be rho Vg anymore, it will be something else. What is? So we can easily write that now the buoyancy force will be rho Vg. It would have been if there was water in the bottom also, but as there is no water, we will write that buoyancy force will be rho Vg minus F2. So this should be our buoyancy force, because F2 was contributing in the upward direction, right? So rho Vg was net in upward direction and F2 have subtracted, because this part we are not getting just because the lack of water in the bottom. So what is F2? Now, F2 is very simple. It is, as it is a horizontal surface, we can write the pressure value at this level and multiply it with the surface area. So in diagram we have given that this surface is at h depth. So here pressure will be rho gh into surface area is s. So the buoyancy force will be rho vg minus rho gh into s for this body. And for this body, similarly, if there was water all around this body, the hydrostatic forces would have acted like this, and we would have gotten a net buoyancy force in upward direction, let's say B dash, that would have been rho Vg as well. But as these forces are absent, these forces are not there, so buoyancy force will increase because these downward forces was counterbalancing buoyancy. But if we remove these forces, it will enhance the magnitude of the buoyancy force. So the new buoyancy force will be nothing but rho Vg plus the forces that we have removed. Imagine that we have removed these forces. So that value will be again rho Gh into S, right? So this is the B dash value for this body. Now I will write this in a clear manner. I just wrote all these steps to make you understand that buoyancy force is not always the volume of the volume of the water displaced. So I'm erasing all these steps and we'll draw the diagram again. Just wait a minute. Let me erase this. Okay. So this was the catch, I guess. I think next you can do. I'll explain, not to worry. But that was the major concept, that buoyancy is not always the weight of the displaced fluid. Okay. So this is the body 1 of rho 1 density. It is having the buoyancy force in upward direction B, and its value is rho Vg minus rho Gh into S, and its weight is acting downward. Its weight is rho 1 Vg, and as there is glue attached between the two layers, so the two layers will try to detach each other there, but the glue will keep it intact. So the glue force is F. As we are solving for the limiting case, we are assuming that a glue force is acting at its maximum value, that is F, and we are given, I think, the value of F, yeah, 500 Newton. So basically this is the free body diagram of the first body, and we can similarly draw the free body diagram of other body as well. Let me draw once. This is the rho 2 density body, and its net buoyancy force is upward as rho Vg plus rho Gh into S. Its weight is acting downward as rho 2 Vg, and its glue force will be upward just to keep it intact with the first body. As you can understand that if H value can change, the buoyancy force value will also change. So at a certain point there will be a condition when the glue force will not be sufficient enough to keep these two intact. So that's the thing question is asking us. So you can solve from any one of the free body diagram, right? So I'm solving from the first part only. So just balancing all the forces, and it will sum up to 0 as it is in vertical equilibrium. I mean total equilibrium also, but we have we have shown only the vertical forces. So the upward forces are rho Vg minus rho Gh into S, and the downward forces are rho 1 Vg plus F. So from here on we will get rho Vg, we're supposed to find H, right? So let's keep rho Ghs terms one side and other terms on the other side. And now let's proceed with rho Gs into H, and now I'm using the value of rho. Here we have already found out the value of rho as rho 1 plus rho 2 upon 2. Let's put it here, minus rho 1 whole multiplied by Vg minus F. So it's now just simple calculation, I guess. rho gs into a. So this one will be rho 2 minus rho 1 upon 2 vg minus f. Now you take the LCM as well, with combining with the term f1. So it will be rho 2 minus rho 1 vg minus 2f upon 2. So h will be rho 2 minus rho 1 vg minus 2f upon 2 rho gs. Oh wait, have I done some mistake? Oh no, it is just the row value you need to put here. That 2 row will be rho 1 plus rho 2, right? Because the row was rho 1 plus rho 2 by 2. This is the vg minus 2f on rho 1 plus rho 2g into s. So that's the answer. Basically this is not h, I should say this is the maximum minimum depth of h in the liquid, so that the common flat portion be in equilibrium and keeping the objects intact as well. So this is basically h minimum, and I'm not going to put the values, and I'll just write the final answer once. Wait, let me check the final answer from the book once, and I will write it here. Wait. Yeah, so putting all the values, you are given rho 1, rho 2, v, g and f, you will get this as 10 meters. So this is our answer for this question. So I hope it has helped you. By if there was some misunderstanding regarding the buoyancy force, it must be get cleared, or otherwise also it's a very good problem to come across, I guess. So that's all for today, and thank you.